For centuries, brilliant minds grappled with a fundamental question: what is light? Is it made of tiny little particles, like miniature bullets, zipping through space? Or is it a wave, rippling and spreading like the waves you see in an ocean? This wasn't just an academic debate, it cut to the very core of how we understood the universe. In the early 19th century, a British polymath named Thomas Young decided he would finally settle the score. His simple, yet profound, experiment would forever change our perception of light, and unknowingly, lay the groundwork for a much bigger mystery. In his dimly lit laboratory, around 1801, Thomas Young set up what would become one of the most famous experiments in physics. He took a single beam of light and directed it towards a barrier with two tiny, parallel slits cut into it. The light that passed through these slits then hit a screen behind. If light were purely particles, he reasoned, you'd expect to see two bright lines on the screen, matching the slits. But what Young actually saw was something entirely different: a pattern of multiple bright and dark bands, an interference pattern. This interference pattern was the unmistakable signature of waves. Just like water waves passing through two gaps will create new waves that constructively and destructively interfere with each other, light was doing the same. Where wave crests met crests, you got a bright band. Where crests met troughs, they cancelled out, creating a dark band. Young's experiment seemed to definitively prove it: light behaved like a wave. Case closed, right? For a time, yes. Scientists embraced this understanding, confidently categorizing light as an electromagnetic wave. But the universe, as it often does, had a few more surprises up its sleeve. Fast forward to the early 20th century, and the world of physics was buzzing with new discoveries. Scientists were peering into the unbelievably tiny, subatomic world, the quantum realm. Here, the rules of our everyday experience simply broke down. Things behaved in ways that defied intuition, logic, and sometimes, even sanity. One of the biggest challenges came from understanding electrons, the tiny particles that orbit atomic nuclei and carry electric current. Common sense told us electrons were definitely particles, solid little bits of matter. They had mass, they had charge, and they could be detected as individual specks. Inspired by Young's work, physicists wondered, what if we sent individual electrons through a double slit? If electrons are particles, surely they'd behave like tiny little marbles. Fire them at a wall with two openings, and you'd expect them to go through one slit or the other, creating two distinct piles on the screen behind. It seemed like a straightforward experiment. But this is the quantum world, and straightforward is rarely how things play out. The results, when they came, were utterly bewildering, completely upending everything scientists thought they knew about particles. When physicists sent individual electrons, one at a time, through the double slit, they didn't see two distinct bands. Instead, over time, as more and more electrons hit the screen, they built up an interference pattern. Just like light. This was impossible. How could individual particles, fired one by one, interfere with each other? It was as if each electron passed through both slits simultaneously, then interfered with itself. Imagine firing a tennis ball at two open doors and having it create a wave pattern on the wall behind. It made no sense in our macroscopic world. This experiment, often called the most beautiful experiment in physics, revealed the bizarre concept of wave-particle duality. Subatomic particles, like electrons, weren't just particles, and they weren't just waves. They seemed to possess characteristics of both. But the truly mind-bending part wasn't just that they acted like waves, it was when they decided to do it. It seemed as if the electrons knew whether we were watching them or not. This led to the next logical step, trying to figure out which slit each electron went through. Physicists, naturally curious, decided to place detectors right at the slits. Their goal: simply observe which path each electron took. Did it go through the left slit, or the right? They weren't trying to interfere with the electron's journey, just to see it. It seemed like a perfectly reasonable attempt to solve the mystery of the interference pattern. With these detectors in place, they started the experiment again, firing electrons one by one. The expectation was that now, with a clear path recorded for each electron, the wave-like behavior would vanish, and the particle would show its true colors. And that's precisely what happened. The moment a detector was placed at the slits to observe which way the electrons went, the interference pattern vanished. Instead, they saw two distinct bands on the screen, exactly what you'd expect from particles acting like tiny marbles, each going through one slit or the other. It was as if the electrons knew they were being watched and decided to behave normally as particles. Remove the detectors, and the interference pattern reappeared. Put the detectors back, and it vanished again. This wasn't just strange, it was profoundly unsettling. So, what exactly constitutes observation in the quantum realm? It's not necessarily a conscious mind looking. Any interaction that gathers information about a particle's state or path counts as an observation. Even a stray photon bouncing off an electron and hitting a detector, or a tiny magnetic field influencing its trajectory, is enough. The act of measurement, of gaining which path information, fundamentally alters the system. It collapses what's called the electron's wave function, forcing it to pick a definite state, to commit to being a particle at a specific location. Before observation, a quantum particle exists in a state of superposition, a blend of all possible states simultaneously. It's not definitively here or there, not definitely a wave or a particle. It's both, and neither, until we look. Imagine a coin spinning in the air. Before it lands, it's neither heads nor tails, it's a superposition of both. Only when it lands, or when you force it to, does it commit to one definite outcome. Quantum particles behave similarly, but with far more profound implications for the nature of reality itself. This is where the double-slit experiment truly challenges our intuition. It suggests that reality, at its most fundamental level, isn't fixed or objective until it's measured or observed. The electron doesn't have a definite path until we try to find out its path. It doesn't choose to be a particle or a wave, our interaction seems to force that choice upon it. This isn't just about tiny electrons, it implies a deep connection between the observer and the observed, a relationship that is absent in classical physics and deeply unsettling to many. This phenomenon is famously known as the measurement problem in quantum mechanics. It's one of the biggest unresolved puzzles in physics. What exactly constitutes a measurement? Where does the boundary lie between the quantum world, where superposition reigns, and our classical world, where things have definite properties? Some theories suggest consciousness plays a role, while others argue that it's purely a physical interaction, regardless of whether a conscious entity is involved. No one fully agrees, and the debate continues to this day. If you thought it couldn't get any weirder, consider the delayed choice experiment. In this variation, scientists decide whether to detect the electron's path after it has already passed through the slits. And remarkably, the outcome is the same. If you decide to measure which path it took, even retroactively, the particle behavior emerges. If you decide not to, the wave behavior persists. It's almost as if the particle somehow knows what information will be gathered about its past, even if that decision is made in its future. It further blurs the line between cause and effect. To really grasp the strangeness, let's contrast the quantum world with our everyday, classical world. In our macroscopic experience, an apple has a definite color, shape, and location whether you look at it or not. Its existence isn't dependent on your observation. But in the quantum realm, the fundamental particles that make up that apple don't seem to operate under the same rules. They exist in a haze of probabilities until an interaction forces them into a concrete reality. It's a stark reminder that our intuitive understanding of the world doesn't always apply at its smallest scales. The double-slit experiment isn't just a quirky parlor trick for physicists. Its implications ripple through almost every aspect of modern technology and our philosophical understanding. From quantum computing, which harnesses superposition to perform calculations far beyond classical computers, to the very nature of consciousness itself, this experiment forces us to re-evaluate what we mean by real. It's a reminder that the universe is far stranger and more fascinating than we could ever imagine, and that our role within it might be more active than we perceive. It's important to reiterate that observation doesn't necessarily mean a human looking. It means any interaction that can extract information. Even if a detector is set up and no human ever checks its results, the potential for that information to exist is enough to collapse the wave function. The universe, in a sense, observes itself. This shifts the focus from a conscious observer changing reality to the fundamental interconnectedness of all particles and fields, where interaction itself defines reality. Despite decades of research and countless experiments confirming its results, the double-slit experiment and the role of observation remain one of the deepest mysteries in quantum physics. There is no single, universally accepted explanation for why particles behave this way. It forces us to confront the limits of our classical understanding and embrace a reality where certainty is an illusion at the smallest scales, and where the act of looking can indeed sculpt the very fabric of existence. The journey to understand continues.